Bismillahirrahmanirrahim. I am Dr. Sarfaraz Ali, uh, lecture select number 10, with the course title Introduction to Riemannian Geometry. I am from Faisalabad campus. Okay. Our first topic is Serret Frenet formulae. Here is the vectors t, n, the vector t, the vector n, and the vector p. All three vectors are perpendicular to each other. Actually, this t denoted by tangent vector. This is normal, and this is binomial. And you are well known to them. From the right-hand system, these three equations, we have to prove t prime is equal to kn. K stand for curvature, n is normal. Second, n prime is equal to tau b minus kappa t. Tau is torsion, b minus kappa t, and b prime is equal to minus tau n. And from basic vector analysis, we know that if we have ijk, three coordinates, similarly we have t and b in cyclic order, and their product b cross t mean from here b cross t is equal to n. This is b cross t is equal to n vector, and t cross n is equal to b, and in the same way n cross b is equal to t. As you know guys, if we use anticyclic, then there will be the negative sign. N cross t will be minus b, b cross n will be minus t, and t cross b will be minus n. And similarly, t dot n is equal to 0 as I dot j is equal to 0, j dot k is equal to 0, and these three vectors are behave just like ijk. So t dot n is 0, n dot b is equal to 0, and b dot t is equal to 0. And when we take dot product with each other, then n dot n is equal to 1, t dot t is equal to 1, b dot b is equal to 1, and uh, this term become a square. N dot n is n square is equal to 1. Uh, t dot t is equal to 1, b dot b is equal to 1, and here it is written wrongly. N cross n is 0, t cross t is equal to 0, and b cross b is equal to 0. It's a composing mistake. Okay, now we have to prove all these three formulas mean, as we have t prime is equal to kt in previous, mean we are here. We have to prove t prime is equal to kn, n prime is equal to tau p minus kt, and d prime is equal to minus tau n. We are proving these terms. Okay. From this term, let we have an arc length, this one. It is delta s, and this is a tangent vector. This b is considered as origin and from B to D to E. This is a tangent vector, and there is a certain change in T, mean from this delta T. So this vector become T plus delta T, mean when we change from E to F, when we change this R from this tangent E to F, this is a change in this one, and this arc is changed from delta S, and this angle is changed as delta theta. So let delta t is equal to EF. From here delta t, this delta t is equal to EF, and delta theta is equal to angle between EBF, mean this angle delta theta is angle between EBF. Also dt over ds mean is equal to limiting case delta s approaching to 0 is equal to EF, mean dt over ds is equal to limit delta s approaches to 0, mean if there is a certain change in arc length, if there is a change delta s approaching to 0, however small, to EF, and this direction is perpendicular to tangent. From here this direction is this direction. From here this is here passing to this one, from here this one. So this delta t or delta s is perpendicular to t. Moreover, be is equal to bf is equal to 1 if we suppose be and bf their magnitude is 1. So also the modulus value of dt over ds is the limiting value of delta theta or delta s, mean from here as this delta s is change, this change is corresponding to delta theta, mean if this is increasing then delta theta is increasing, and if this arc length is decreasing then delta theta is decreasing. So we are here. The modulus value of dt over ds is the limiting value of delta theta over delta s, which is kappa. Hence, dt over ds is equal to limit delta s approaches to 0, delta t over delta s is equal to, that it is equal to some kn, where n is the unit vector perpendicular to t, and in the plane of tangent at P and at consecutive point P. So T prime, mean from here this dt over ds is equal to T prime is equal to this Kn. So our first proof is T prime is equal to Kn, mean actually we are proving here the rate of change of tangential component, yeah, tangent vector is equal to is directly proportional to normal uh, to unit vector n, unit normal vector n with multiplied by k. Okay, this can be proved in other ways. Mean the same result can be proved in second. Let ks is equal to d theta over ds, mean we are supposing here, mean rate of change of angle with respect to rate of change of arc length ds in limiting case is equal to ks. Thus, this the magnitude of ks is equal to d theta over ds. So this k is equal to implies mean k This Kf means sum of all uh, subsections of arc length is approaching to S is K is equal to d theta over dt over ds. Here we use chain rule. So this chain rule is equal to d theta over dt over ds is equal to here this d theta over d, d theta over dt is equal to 1, and this we remained with dt over ds. Why this is 1? As d theta over dt unit vector unit change, so it is 1, its arc length is 1. So this result is equal to t prime magnitude. This is derivative of time tangent vector with respect to s. So this k is equal to t prime vector. Let we call this equation number 1. Also, kappa is equal to t prime is equal to this t prime is equal to r double prime, mean this is a double derivative of position vector r. So we call it equation number 2, this equation number 2. And since r prime square norm square is equal to 1, so this r prime dot r prime is equal to 1. Differentiating this equation with respect to s, this term become 2r prime dot r double prime is equal to 0, as the right hand side is equal to 0. Thus, if dot product of two vectors is 0, so these two vectors are perpendicular to each other. Thus, r double prime is perpendicular to n, as uh, we have supposed before. R prime is a tangent. R prime is a tangent vector, and tangent vector is perpendicular to normal n. So when this r prime is perpendicular to r double prime, then r double prime must be perpendicular to n. So r double prime is equal to kn, mean when we change the perpendicular condition from here, this term r double prime is sorry, this r double prime is normal to n. Sorry, uh, I, I was confused here. R double prime is parallel to n. If these two vectors are parallel, then there must be a relation between them. R double prime must be is equal to kn. For perpendicular, I can use here for drawing. When I am calling here this r double prime is parallel to n. So if this vector is r double prime, let I write it as here. Then this n must be like this one. Maybe it is less than r, maybe it is greater than r, or this line can be dragged this one. So this term is n vector. So there these if these two vectors are parallel, then there is a relation, mean this r double prime is equal to n, and this k must be a number which may be uh, half of the first one, double or triple or whatever, which is the relation between these two. So this term r double prime is equal to k n k. Thus, r double prime itself is equal to t prime k. So our result become t prime is equal to k n from 2, equation number 2. So this is the proof of the equation. Okay, this is our first proof. Now Now, proof of the second. B prime is equal to minus star n. I want to erase this one. Okay, I have to remove this one. So I erase this one from here. So now we are on this term, second term. B prime is equal to minus star n. Consider B dot B is equal to 1 as dot product with each other is equal to 1. Differentiating with respect to S, we differentiate this one B dot dB over ds plus dB over ds dot B is equal to this one. Derivative of 1 is 0. So these two terms are same. So it is multiplied by 2 B dot dB ds is equal to 0. This implies that uh, this two can't be 0. So B dot dB over ds is equal to 0. So we have here B dot dB over ds is equal to 0. Okay, this term dB over ds is equal to B prime. So we have B dot B prime is equal to 0. Okay, now if the dot product of two vectors, here are two different vectors B and B prime. If the dot product of two vectors is 0, so these two vectors are perpendicular to each other. Thus B and B prime are perpendicular to each other. Now, dif- uh, no, again we differentiate. We have a next term T dot B is equal to 0. If we take a dot product of two vectors tangent and binormal, this is equal to 0. Differentiating with respect to S this term, so this is T dot dB over ds plus T dt over ds dot B is equal to 0. This become T B prime plus T prime dot B is equal to 0, as in equation number 1. As we know that T prime is equal to K N K, mean kappa N K. So substitute this term from here. So T dot B prime plus K N dot B is equal to 0. So here is dot product of N dot B. This one must be 0. So we remained with T dot B prime plus kappa 0 is equal to 0. So we have T dot B prime is equal to 0. Thus T is perpendicular to B prime. Now we have two results here. B is perpendicular to B prime and T is perpendicular to B prime. If we have, but N is perpendicular to tangent N, but N is perpendicular to tangent T, and N dot B prime is parallel to N. If these are equal to parallel to N, thus B prime is equal to minus tau N, where tau is the measures the magnitude of arc rate of rotation of binormal, and negative sign indicate that vector along the normal but in opposite direction. So our second result is B prime is equal to minus tau N. Okay, no, proof number 3. N prime is equal to dn over ds, meaning this prime is equal to dn over ds is equal to tau b minus kappa t. Okay, consider n is equal to b cross t. It is no problem. N is equal to b cross t. Differentiating with respect to x on both sides, so our first result become dn over ds is equal to b cross derivative of second term dt over ds plus derivative of first term db over ds cross t. So this term become, this is t prime, and this term become d prime. Now substituting the values of t prime and b prime, as these two are our previous results. So we substitute here n prime is equal to b cross Kn plus minus star n cross T. Now from here kappa is a constant, so it is outside the bracket, so kappa into B cross n plus ta n minus n cross T is equal to. So this term B cross n is in anticyclic, so it is minus T plus star. This is anticyclic n cross T. This gave a minus plus B. Here is minus B. That's why it is plus B. So this term become minus kappa T plus star B. And when we arrange them, then n prime is equal to dn over ds is equal to tau B minus kappa T. So these are the three proofs of this term of Serret-Frenet theorem. So there is a next Serret-Frenet transformation matrix. We have three formulas for this one. Ta prime is equal to kappa n, B prime is equal to minus ta n, and n prime is equal to ta B minus kappa T. Then the matrix, this ta prime, B prime, and n prime. So we write them in cyclic order. Ta prime, n prime, B prime is equal. From this term, if we have three terms, this is okay. I again use note, the note here. Text. No, with this one, if we have, this is here some, no, this is T, this is N, and this is V. So if we have first term, this is a component coefficient of T, this is coefficient of kappa n, and this is coefficient of B. And in second term, in third term, we have minus kappa coefficient of T, and second term is 0, and third term coefficient of B is star. This one, and again in from this equation, B prime is here, so 0 minus star 0, and on right side this is star and D. This is the order of these equations. Is called matrix form. Is called the matrix form of Serret-Frenet formula. Let A is equal to 0, kappa 0, minus kappa 0, ta 0, minus ta 0. Then A transpose is equal to uh, interchange the rows and columns. So is equal to minus this one. So A transpose is equal to minus A. So matrix is a skew symmetry. I hope you understand the Serret-Frenet theorem and its matrix form. This is end of the lecture of this term.